So this P4 video is going to be on work and energy calculations. We're just going to look through 3 examples getting increasingly complex of the sort of questions you might get asked. Okay, so the 4 equations that kind of go together when you're talking about work and energy are the ones in the red box here. Okay, and unlike the momentum calculations, which we're often looking at starting and a final situation separated by a certain amount of time, often the work and energy calculations are most useful if you have a starting and final situation separated by a certain amount of distance. Okay, and again, with some of the questions you might only need one of the equations, but the more challenging questions might need you to join several together. So a sort of 4-mark calculation, you'd need to use more than one equation usually. Okay, so let's look at a simple example to start with of a falling object. Okay, so we're going to have an object falling through a distance of 15 meters, and its mass is going to be 0.2 kilograms. Remember, you know its mass because mass is measured in kilograms and weight is measured in newtons. It's going to be very important to keep that in mind when you're doing these questions. So a multi-part question here that leads you through the things to do. How much gravitational potential energy, or GPE, does the ball lose? Well, as soon as we see that, we see that the question is asking us for GPE, and the only equation that's got gravitational potential energy in it is the third one down there. So that's the equation we're going to have to use in some way in this problem. Okay, we're given the vertical height difference. That's on the diagram, 15 meters. We aren't given the weight, so we're going to have to work that out. But we should remember, hopefully, that weight is related to mass, and that each kilogram of mass has a weight of 10 newtons on Earth. So that's 0.2 kilograms multiplied by 10 newtons for every kilogram gives us a weight of 2 newtons. So we now have a situation where we've got one equation, we know 2 of the things, and we can work out the thing that's missing. Okay, and we don't even need any rearranging here, so this is nice and straightforward. We take the 2 newtons, multiply it by the 15 meters, and that gives us a change in gravitational potential energy of 30 joules. We know it's a loss because the ball is falling downwards, and an object which falls downwards is losing gravitational potential energy. So how much kinetic energy does the ball gain? Well, the only way to do that, really, is to actually just look at the amount of energy transferred as the work done equation. It's really just saying that if you lose 30 joules of gravitational potential energy, that must be being transferred to somewhere, and that is the gain in kinetic energy. You might be tempted to use the bottom equation, but note we haven't got any idea what the final velocity of the ball is, so we can't really do that one easily. Okay, but we are making an assumption to answer part B, and that's the assumption that there's no drag forces acting, as if there were, they would take some of the kinetic energy and transfer it into thermal. So that would mean the final kinetic energy would be less than 30 joules. Okay, so that's a simple single equation, really, calculation to get that 30 joules. So let's see what happens if we remove that assumption that we've just used, that there is no drag, and put some drag in. So we're releasing a ball from rest again, and this time we've got a weight of 20 newtons, so you've been directly given the weight, and a drag force of 5 newtons. I'm going to drop that through a distance this time of 30 meters. Okay, so another multi-part question. Same thing to start with as before. How much GP does the ball lose? Now note that the presence of the drag force doesn't affect how much gravitational potential energy the ball loses. That only depends on the weight of the ball and the vertical height. So that's the same procedure as before. The 20 newtons weight multiplied by the 30 meters is 600 joules. This time we don't have to convert the mass into weight because we've already got the weight. So this time though, how much energy is lost as thermal? Well, we've got a 5 newton drag force there, okay, and we're going to be using energy lost as work done, but this time we're going to have to calculate the work done by that frictional or that drag force. Okay, so we need the size of the force, which is 5 newtons, okay, and we need the distance moved in the direction of the force. And again, that force is vertical and it's moving 30 meters. Because the force is pointing upwards and the object is moving downwards, that force is going to be removing energy. So it's going to be dissipating the energy, is the word we use, as thermal. But again, now we have our 2 things in the top equation that we know, so we can calculate the work done by the force. It's the 5 newtons times the 30 meters, giving us 150 joules. So that is how much energy is transferred as thermal. We've now turned all the things in the equations green. We know all of them. Okay, so this time, what's the final kinetic energy of the ball? Well, there's not an equation for this, again, because we don't know the velocity yet. We're actually going to use the kinetic energy in part D to work out the velocity of the ball. So you just have to think in terms of energy transfers. If we've lost 600 joules of gravitational potential energy, then in the previous question, that would have given us a gain of 600 joules of kinetic energy, but this time 150 of it has gone into thermal energy. So the kinetic energy is the difference between the GPE lost and the thermal energy lost, and that gives us 450 joules to go towards kinetic energy. So that's the kinetic energy of the ball at the bottom of its drop of 30 meters. Now, the last part here, the final speed of the ball, is one of the tricky ones to do because the kinetic energy equation is more complex than the other equations that you have to use. You can use the triangle method very simply to rearrange the other equations. And again, if you haven't looked at that and you're not confident, go and look in the GCSE skills playlist on the channel and you'll see the triangle method there. Okay, so the way to do this is by using the kinetic energy equation, because if we're asked for the final speed of the ball, what we're really after is the velocity. In the kinetic energy equation in particular, more than any other of the equations, it's perfectly okay to swap speed and velocity around, okay? Because that squaring process for the velocity removes any minus signs that might be there. Because a velocity of minus 3 squared is 9, a velocity of plus 3 squared is also 9. So we don't really care about the direction aspect of the velocity when we use it in the kinetic energy equation. So, the final speed of the ball. Well, we need to know the other things. So we need to work out the mass, which we haven't been given this time, and we've just worked out in the previous part of the question what the kinetic energy is. Do remember that the previous parts of questions often help you with the next part. Okay, and if you get stuck and you can't work out a previous answer you need, if you just make up an answer and use one, you will get what's called error carried forward marks. You'll get the marks for the working of the last part, even if you're not sure about the numbers you needed to use in it. Okay, so there's our kinetic energy. So I'm going to do the working for this down the side. First thing is we need to find the mass. This is kind of like what we did in reverse to find the weight. We know that each Newton, right? Each 10 newtons, sorry, is 1 kilogram of mass. So we take the 20 newton weight, we divide it by 10 newtons per kilogram this time to give us our 2 kilograms of mass. Okay, that makes sense because the 2 kilograms, each of those is 10 newtons. There's our 20 newtons of weight. So we've now got our mass, so we can turn that green. So we now have our equation with velocity in there and mass and kinetic energy, and obviously we know the half. So we can theoretically now work out the velocity. And it's just a question of rearranging the equation. So there it is written out again. Kinetic energy is half times the mass times the velocity squared. We want to get rid of that annoying half, and to get rid of a half, we multiply by 2. And remember, you can do this, as long as you do the same thing to both sides of the equation, it will stay equal. And so you can do whatever you like as long as it's the same thing to both sides. So I multiply both sides by 2. That gets rid of the half on the right-hand side of the equal sign and gives me a 2 times kinetic energy on the left-hand side. The next thing we want to do, because we're trying to get velocity on its own, is to get rid of the mass from the right-hand side. And in order to do that, we need to divide by the mass, because we've got mass times velocity. If we do that, we get rid of the mass from the right-hand side, and we end up with twice the kinetic energy divided by the mass on the left-hand side. And then the final thing to do is to get rid of the squared, and to do that we do the opposite of squaring, which is taking the square root. And you've got to remember to take the square root of the entire other side. Okay? Now, if you are not confident about rearranging equations, but you're quite good at remembering them, then it might be worth remembering that velocity is the square root of twice the kinetic energy divided by the mass. Okay? Now, when you do this, make sure you do the things in the right order in your calculator. Work out the bit under the square root sign first, and the final thing you do is the square root. So we've got twice the kinetic energy, 2 times our 450, divided by the mass, okay, which is also 2. So the thing under the square root then is going to be 450. We then take square root of 450 to give us 21.2 meters per second. And there's your answer. Those kinetic energy used to find velocity questions are some of the ones that people find trickiest. So if you think that's a bit difficult, then watch it back again, okay, and just make sure you've got it down. Because if you can do that, you'll be at a significant advantage to other people doing the paper. Okay, final example. Not really any harder than this one. It's just a slightly different way of framing the question. It looks more difficult, but as long as you keep your wits about you, you'll be fine. This will be at the absolute top end of the spectrum in terms of difficulty of these questions, okay? So if you can do this or understand going through it, then you'll be really set. Okay, so the same thing really as before. We've got a box sliding down a slope. So the complication here is we've got a few more forces acting. We've got normal reaction as well, and we'll talk about why that one doesn't really matter in a second. And this time it looks harder because the forces are all pointing in different directions. And if you were trying to do this with resultant force and work out what happened there, it would be really hard to do it and you need some complex maths. But here, as long as we're careful, we just need to do some multiplying and the kinetic energy bit at the end will be fine. So, first part, how much GP does the box lose as it slides down the slope? Well, remember, the only thing that matters for gravitational potential energy change is the vertical height difference. So we just need to make sure we're using the vertical height. Okay, so the vertical height on the diagram is 3 meters and the weight is 20 newtons. I've not highlighted the equations again for this one, so you can see if you can follow it yourself. Okay, so our change in gravitational potential energy is 60 joules. We've lost 60 joules from that box sliding down the slope. Okay. How much energy is lost to thermal as thermal to friction? Well, this time, okay, our frictional force is 1 newton, so that's our drag force. But we have to be very careful. If you look at the work done by a force equation, it's force times distance moved in the direction of the force. And the frictional force is pointing along the slope. So we don't want to use the 3 meters here because that's not the direction that the frictional force is pointing in. We need to use the 12 meter length of the slope that we've been given. So the thermal energy lost now is the 1 newton of frictional force multiplied by the 12 meters that force has moved through, giving us 12 joules. Okay, so that's just a slightly different way to get the thermal energy that you have to be careful of, but then the idea of how much kinetic energy the box has at the bottom is exactly the same as before. We take the gravitational potential energy lost, we remove the dissipated thermal energy, and that leaves us with 48 joules of kinetic energy at the bottom of the slope. And then the final part, again, we need to work out the mass. Again, I've used the same weight, so it's a 2 kilogram mass for that 20 newton weight. And the same equation, I won't do the rearranging again, but this time just with a different kinetic energy. And it turns out it's the same mass, but it could be a different one. So again, we just put those numbers into the equation and we can get 6.9 meters per second out. So as long as you're careful, that slope problem is really no harder than the ball dropping one, right? And this is an important point that with any calculation, especially if we don't have one with friction, we don't really care about how the object got from the top of the slope to the bottom. So this is why you can use this energy method for really complicated things like roller coasters, where the path that's being taken is very complex. If there's no friction there, you don't even care about the path at all, or even how long it is. All we care about is the vertical height difference and converting that GP into kinetic energy. So there's some example calculations, some quite tricky ones. If you can follow those through and try and reproduce them properly in the exam, then you'll do extremely well.